Enceladus is one of the over 60 moons that orbit Saturn. It forms Saturn's E ring, the outermost ring, which is primarily composed of ice emitted by Enceladus. Originally discovered in 1789, data on Enceladus has been collected from numerous missions. Flybys by the Cassini spacecraft indicate that Enceladus has an ocean. Details of this data, as well as analysis and conclusions drawn by Postberg et al., will be discussed in this video. It has been discovered that there's a plume of water vapor and ice particles emerging from these stripe-like fractures, called sulci, on the moon. This raises the question of whether the matter that composes the plume is supplied from a subsurface liquid source or from the decomposition of ice. The presence of liquid water has already been indicated by previous compositional analyses of particles ejected from the plume, and new data strongly suggests that a salt-rich reservoir with a large evaporating surface provides nearly all of the matter in the plume. Though non-liquid models have also been proposed, the new data renders them highly unlikely. During 3 transversals of the Enceladian plume, Cassini's Cosmic Dust Analyzer, CDA, produced time-of-flight mass spectra generated by high-velocity impacts of individual grains onto the metal target. There are 3 types of particles detected that we'll be focusing on. Type 1 particles are water-rich. Type 2 particles are composed of organic and/or silicaceous material. And Type 3 particles are salt-rich, containing 0.5 to 2% sodium and potassium. The composition of these salt-rich grains closely resembles the predicted composition of an Enceladian ocean that has been in prolonged contact with the rocky core of the moon. Because of this compelling compositional match, the grains are thought to form from frozen droplets present as a spray over the liquid reservoir close to the surface. The Cosmic Dust Analyzer collects data on the particles as it crosses the plume. From 15 seconds before closest approach until about 18 seconds after, salty Type 3 particles increase in abundance. Also during this interval, Types 1 and 2 particles decrease in abundance. The gap in the readings is due to an overload of electronics on the Cosmic Dust Analyzer, resulting in limited viable data collection during the interval of 18 to 35 seconds after closest approach. So, particles have been detected, but what about their origins? The salt-rich Type 3 particles from the plume can either be derived from the jets or a diffuse source, evaporation from the reservoir. The percentage of each type of salt is largely dependent upon the altitude above the South Pole. At lower altitudes, plume composition is supplied almost entirely from diffuse sources. Above 50 kilometers or so, the contribution from each source becomes more balanced. It is indicated that grain velocity decreases with size. This would lead to compositional stratification of the plume, with an observed increase in the proportion of salt-rich grains closer to the surface. Since salt-rich grains are the heavier type, they are present predominantly in the lower portion of the plume and would not escape out into the E-ring, thus explaining why the E-ring is relatively depleted in salts. Of course, further research will be needed to better understand these processes, but based on the data available, Postberg et al. Are able to conclude that one or more saltwater reservoirs with large surfaces of evaporation provide the majority of the matter that composes this plume. The vapor plume issuing from Saturn's ice moon Enceladus is just one of the many wonders of our solar system that we, as scientists, will continue to study.